Let's return to the square loop. Why am I getting a square here? Well, I'm double iterating. So for each value of I iterate through j n times. So the number of pairs, ij, it's the square of n. If I can do this for 2 loops, I can do it for 3. Let's put a third variable k into the mix and see what we get out. Well, first of all, note that my picture has gotten wonky. It's just gone on. And that's because I didn't put any kind of line breaks. To visualize this effectively, you really need 3-dimensional output, because what we're doing here is a cube. And in fact, that's reflected in the results I get. So for 1,000 inputs, I get the cube of 1,000 or a billion. And note that that's taking already, just for 1,000 inputs, it's taking 1 second on my machine. For 2,000 inputs, it's taking 8 seconds on my machine. What's the ratio between these? 8. And why does that make sense? Well, let's think about it. If I have some input in, and that gives me an output, when I double in, I've got 2 times in there. So what is that going to be? For a cubic function, we'd expect the output to go to 2 to the 3rd power whenever I double the input size. Why is that? For 2 in going in, I'm going to get 2 cubed and in cubed going out. So 2 cubed is 8. Thus, we're seeing a ratio here of one problem to the next. As I double the input size, the time it takes goes up by a factor of 8. This is characteristic of a cubic function. Note that in absolute terms, my performance now is truly dreadful. With an input size of only 4,000, it's taking 30 seconds on my machine. Just like squares are related to triangles, cubes are related to pyramids. To create such a pyramid, all I need to do is change the bounds of my inner loops to the induction variable value of my outer loop. So here I will bound j by I, and I'll bound k by j. Before I run this code, let's remember the absolute values that I was getting over here. So for 4,000 inputs in the cube, it was taking about 36 seconds. I'll be back in 6. Well, actually, it took 7 seconds, but the point is made. We're going about 1/6 the amount of time. That's reflected in the results I'm getting. I'm getting 1/6 the value. The geometry here is a little bit more complicated, but if you think about a cube, when you sort of slice it in one dimension and then slice it in the other, you end up with a pyramid, and that's 1/6 of a cube. Of course, I can play this game in 4 dimensions as well. Well, here's a 4-dimensional cube, and you can see here, the ratios now are 2 to the 4th, which is 16, because I'm going in 4 dimensions. For an input size of 200, my computer's taking about 3 seconds. What would it do for a triangular version of this code? Well, it's taking about 1/24th the amount of time it took for the 4-dimensional cube. So my 4-dimensional pyramid is 1/24th the size of my 4-dimensional cube. For input size 200, it's taking a little less than a second on my machine. You can see that the ratio between this 4-dimensional pyramid and the 4-dimensional cube is 24 by looking at the instrumented value. This value here is about 1/24th of the value we got for the 4-dimensional cube. Why 24? Well, 24 is 6 times 4. And what we're actually getting here is factorial. So 24 is 4 factorial. Why is that popping up? Well, the exact mathematics is beyond the scope of this class. But for the kinds of pyramids we're doing, where each loop depends upon the bound of the previous loop, you're going to see this kind of factorial reduction in the size of the pyramid relative to the cube. The triangle is half the square. The pyramid is a half times a third. That's 1/6 of the cube. And the four-dimensional pyramid is 1/2 times a third times a fourth. That's 1/24 of the four-dimensional cube.